TCP stands for the Transmission Control Protocol. In this video, I'm going to provide an overview of TCP. The details will follow in other videos. TCP is a very widely used protocol. In fact, it is so popular that the entire Internet Protocol stack, also called suite, is called the TCP IP suite. And because of its popularity, it is also a very carefully tuned protocol. In fact, there are many requests for comments that cover TCP. So what are these RFCs? I never told you about them before, so let me spend a little bit of time. So there are these bodies called IETF, which stands for Internet Engineering Task Force, and the Internet Society. So these bodies develop the technology and standard for the Internet. RFCs are basically publications put out by these bodies. So if they have some information to share or some new concept to discuss, they basically put it out as a request for comment, whereby the other peers in the community can comment on it, then it undergoes revision, and some of these RFCs could be standardized as well. And there are tons of such RFCs covering each and every aspect of TCP. Unlike UDP, which was a connection-less protocol, TCP is a connection-oriented byte stream protocol. What do I mean by these terms? Connection-oriented means that a connection has to be established before the data can go from one process to the other. Byte stream means the message exchange between the application process and the transport layer is via bytes. So typically the application process write bytes into the TCP send buffer, and the TCP is going to assemble these bytes into segments and pass them on. And at the receiving side, these segments are written in this TCP receive buffer from which the application is going to read the bytes. So for example, if the application wrote 500 bytes, then this may be sent as 500 bytes in the segment. But if it wrote 10 bytes followed by another 200 bytes followed by another 300 bytes, then it may wait to gather enough bytes and send these bytes out in this segment as 510 bytes. And this application process, when it is reading these 1010 bytes that are written here, may read 100 bytes at a time. So to contrast this, one could also pass messages as blocks, message 1, message 2, so on, and this TCP could take these messages and pass them to the other end, which in turn will pass the messages back to the application process. So this is not following this paradigm. So here are the services offered by TCP. Like any other transport layer protocol, it does provide multiplexing, demultiplexing service. In addition to this, this also provides reliable point-to-point data transfer. It is also a full duplex protocol, by which I mean is if you want to send data between A and B as well as B to A, the same connection can be used to send data in either direction. You don't need two separate connections. Another service provided by TCP is that of flow control, where a receiver is going to control the sending rate of the sender. For example, if you have a very fast sender, whereas the receiving process is not reading data fast enough from the receive buffer, the receive buffer can overflow. In this case, you use flow control, whereby the receiver stops the sender from sending too much data. We will cover more of this later. While flow control stops the sender from overwhelming the receiver, the congestion control stops the sender from overwhelming the network. So it ensures that the senders are not sending data at a faster rate than the routers can handle. This in turn can lead to buffer overflow at the routers and dropping of packets. So congestion control ensures that such a thing doesn't happen. Well, to the extent possible. So at the heart of TCP is the sliding window protocol that we have seen earlier. The majority of these services are provided in this context. Remember what the sliding window protocol is? So this picture should help. So we have a window of packets that the sender sends. So this is the window of packets. And in response to this, the receiver is going to acknowledge the packets, and in response to these acknowledgements, you are going to clock out more packets. So as part of the sliding window protocol, we have seen the use of sequence number, acknowledgements, timeouts to provide reliability. So the sliding window protocol that we have seen at the link layer, where we employed this over a single hop, versus the sliding window protocol that we are employing at the transport layer, where the sending and receiving processes may be separated by many nodes in between. So you have to traverse many hops to reach the other endpoint. So this is at the link layer and this is at the transport layer. So given this, can you think of at least two ways in which the sliding window at the transport layer differs from sliding window at the link layer? I'm not talking conceptually, I'm talking more about what challenges will it pose implementing sliding window at the transport layer. Quite a few challenges. One is related to connection management. So when you have sliding window at the link level, the link over which you are running the sliding window is a dedicated link with connecting these two hosts. So when you send packets from this host, they are destined to this other host. And it is easy to figure out the status of this other host. For example, if when I'm in a room with one other person and I'm talking, and if you rule out the possibility that I'm mad and not talking to myself, this means that whatever I'm talking is for the other person. On the contrary, when you do sliding window at the transport layer, you can run this TCP protocol on any processes running on any two hosts in the internet. And you have no idea whether the other host is alive, listening, so on and so forth. So for this, you need explicit connection establishment before you can send data as well as tear down after you're done. That is, you need this in case of doing sliding window at the transport layer. Round trip time RTT is another challenge. At the link layer, this round trip time is almost constant. There may be some slight variation, but the variation will be very small. Whereas at the transport layer, the round trip time will vary from connection to connection. That is, for example, if I have a connection to some other host within Mumbai and another connection to some other host in New York, the round trip times I'm going to see across these two connections will be different. Not only that, within the same connection, this round trip time over time will be highly variable, depends upon the congestion that is there as part of the network path. So in case of transport layer, this timeout mechanisms that we use as part of the sliding window protocol have to be very adaptive to what is happening in the network. The other issue is reordering. At the link layer, there will not be any reordering, whereas at the transport layer, because the packets can take different paths and suffer arbitrary delays, there is scope for reordering. So you need to ensure that the protocol is robust against old packets suddenly showing up in the middle of a new connection. So I mentioned flow control before. When you do sliding window at the link layer, you can definitely engineer the two endpoints to support the link. What do I mean by this is, if you have this link, you know the bandwidth delay product of this link because you have set up the link between these two endpoints. Thereby you can choose the window size appropriately. Whereas if you're doing sliding window at the transport layer, any kind of computer can be connected to the internet. So it could be a dumb terminal which cannot allocate more than, let's say, 4 kilobytes for the receive buffer, or it could be a latest computer in the market that doesn't mind allocating 1 megabyte for the buffer. So if at the sending window size, if you are using 1 megabyte, then you're going to overwhelm this dumb terminal. So you need mechanisms to ensure that one side doesn't overwhelm other side resources. This is part of the flow control. So similar to that, in terms of congestion control at the link layer, it is not possible to unknowingly congest a link. You know what you are sending on that link. Whereas at the TCP layer, which is at the transport layer, you have no idea what links will be traversed by your packets. And not only this, the bandwidth on these links can dynamically vary over time due to competing traffic. So you need mechanisms to alter the sending rate based on the state of the network. If it is not congested, maybe you can send at a higher rate. If it is congested, you have to cut down your sending rate. So what this means to the sliding window protocols is the window is not constant. It will have to vary over time. A good time to break. Up ahead, we will look at the TCP header. So compared to the UDP header, what do you notice? Lot more fields, right? So the source port and the destination port are essential for multiplexing, demultiplexing. So TCP also supports them. As part of the sliding window protocol, you need sequence number and acknowledgement fields. So these fields account for that. Earlier, when we talked about sliding window protocols, we said a packet has sequence number 0, this next packet has sequence number 1, so on and so forth. But things are handled differently by TCP because it's a byte-oriented protocol. So let me get into the details. In TCP, each byte in fact has a sequence number. And if you have a segment that is carrying some data as part of it, the sequence number field that is as part of the header is going to contain the sequence number of the first byte as part of the data. And similarly, the acknowledgement field that you are going to carry as part of the segment is going to acknowledge data of the flow from the other direction. And another twist with respect to TCP is that this acknowledgement field is going to carry the sequence number of the next byte this particular host is expecting. I think an example will make things clear, but before I get there, unless otherwise specified, the TCP ACK is considered to be cumulative. So let's look at this example. In this example, both A and B want to exchange data with each other. And in the past, maybe a few other segments were exchanged. Currently, we are focusing on this particular segment. This segment has a sequence number 20 and the data, that is the payload of this segment, is 1000 bytes. So what this means is out of this 1000 bytes, the first byte sequence number is 20. And this segment is acknowledging some data that was in the past sent by B. And the fact that it is saying 857 means that A is asking B to send data starting at byte 857. So in response to this segment, B is now going to send a segment. So this is the segment that it sends. Since it is asking for 857, so this segment starts at 857. And this segment, the payload in this is 100 bytes. And see this acknowledgement. It is acknowledging this segment, whereby because this byte starts at 20, this is of 1000 bytes long, it is now asking for this byte which is 1020. So that is how the acknowledgements work. So in response to this segment, A is now going to send another segment. So you tell me what is the sequence number of that particular segment? And what is the ACK field of that particular segment? Well, the sequence number will be 1020 because this is what B is asking. And you are acknowledging this particular segment where again this is 100 bytes, this first byte is 857 and you want this byte which turns out to be 957. So that's with sequence number and acknowledgement. Following this is the header length. So you specify what is the header length. You need to specify this because there are options here. In case there are no options, the TCP header length is 20 bytes. Then there is this reserved field which is set equal to 0. Following this are the flags. So let's look at flags UA, PR, SF. So U here stands for the urgent flag. So whenever this flag is set in a segment, it is indicating to the receiver that there is some urgent data as part of the segment and thereby pass this data to the application right away. And this urgent field is associated with an urgent pointer. So that's here. And this urgent pointer specifies where in the segment non-urgent data begins. So there is an assumption here that the urgent data begins right after the header. And this specifies in bytes what is the length of the urgent data. This A flag is the acknowledgement flag. So whenever a segment carries a valid acknowledgement, this bit is set equal to 1. Thereby, the other end can interpret the acknowledgement field appropriately. So sometimes the data flow is only in one direction, thereby you don't have to interpret the acknowledgement corresponding to the other direction because there is no data flow in the other direction. P stands for push flag. At times you want to indicate to the receiver that whatever data is in the buffer, push it to the application process. So this flag is not used. Similarly, the urgent flag is also not used. R stands for reset. So whenever this flag is set, it is indicating that whichever set this flag wants to abort the connection. Basically, you make use of reset whenever you receive some data which confused your state. For example, some packet with a sequence number that you should normally not see, in which case you are going to reset the connection. Similarly, the SF flags stand for synchronization and finish flags. They are short for SYN and FIN flags. These are used during the connection establishment and termination. We will see more of this later when we talk about connection management. So following the flags is the advertised window. This is part of flow control. So when I cover flow control, I'm going to get into the details. And just like in UDP, you have a checksum field. So this checksum field is compulsory both in IPv4 as well as IPv6 because TCP offers reliable service. And again, much like in UDP, this checksum is calculated over the TCP header data as well as a pseudo header. For the pseudo header, you take the source, destination and protocol fields of the IP header, and not only that, you include the TCP segment total length. Notice that there is no such field as part of the TCP header. This total length actually has to be calculated. So these option fields are used during the connection setup time to negotiate certain parameters, and they are also used later to carry certain information to implement certain functionality. For example, you could use option fields to negotiate maximum segment size. For example, A may tell B that it wants to use a maximum segment size of 1 and B may tell A that it wants to use a maximum segment size of 2, in which case both of them will use min of these two values as the segment size as part of the connection. These maximum segment size have a relation with the MTU that is supported by the network to which these two hosts are attached. By exchanging this information, you basically choose an appropriate value of MSS and thereby an appropriate value of MTU. Now, does this mean fragmentation will never arise at the IP layer? What do you think? Well, no, fragmentations can still arise because this negotiation is being done end-to-end at the process level. Routers are not involved as part of this. This is just an optimization. Options fields can also be used to perform what is called window scaling. So this is part of flow control. So if you see the advertised window field, this is 16 bits, which means the receiver can tell this buffer size, and because you are using only 16 bits, the maximum buffer size that can be accommodated is 2 to the power of 16 bytes. But what if you want to allocate more buffer because you want to operate with a window size that is greater than this? In which case you will use this option fields to indicate, say, a value of 3, whereby you are saying whatever is specified in the advertised window field, you multiply it with 3 to use as the window size. I think this point will become clear only after I cover flow control. We talked about selective acknowledgements before. These are much more efficient than cumulative acknowledgements. Now, if you want to use these features, you can do so using the options field, where at the connection setup, you can indicate that I can support selective acknowledgements, and if both sides agree, henceforth they can use selective acknowledgements. And the actual selective acknowledgement data information is also carried as part of the options fields during the data transfer. Similarly, the checksum that is employed as part of TCP is not a very sophisticated algorithm. It is a function of the 16-bit once complement algorithm that I mentioned earlier. But if you want to use a more powerful checksum, options fields let you use a more powerful checksum. There are more options than this, but I think you get the idea as to how options fields are used. So to summarize, TCP is a very popular finely tuned protocol. It provides quite a few features: reliable data transfer, full duplex operation, flow control, congestion control, so on and so forth. At the heart of TCP is the sliding window protocol. We also examined the TCP header. Up ahead, we will see how the TCP establishes connections as well as tears them down under connection management.